Okay, so we fold this in half. Okay. Now I want you to fold the bottom maybe like an inch, about an inch. Doesn't have to be exact. Okay. And you want to mark right at the top where they meet. Put a dot. Right at the top where they meet, so you can unfold it and the dot still stays there. So it's almost exactly right on it. There we go. Okay, next. You're going to fold this many, many times. Okay, so here's how you fold it. Just take one edge, pull a corner up, and crease it, unfold it, and then just go at another angle that's maybe very close to it. Get very close to the dot once again. Don't go over it. Okay, crease it again. So this little point here is kind of leading how you fold the paper. So you just keep on unfolding and refolding according to this one little dot. Okay. And the mathematical term, what you're doing right now is that you're making a perpendicular bisector over and over and over. Okay, which you'll hear a lot of in geometry. But that's what all these folds have in common. Okay, now you can even get vertical, like right here. Right, like a 90-degree fold. And then you can fold it this way as well. So you can keep on going like so. Unfold, refold, many times as you can. And then once you're done with one side, do the same thing on the other side. So fold it over. Okay, so by the end of it, after enough, you don't have to have too many, but you can start to see along the top here, if you follow the top of all your folds, it kind of looks like this. Okay. And it won't be perfect, but it'll be pretty spot on. Okay. Yep, you can go ahead and draw it on just like I am. And this shape is a parabola. Okay. Parabola. And this is what, when we start looking at what you guys were just working on, if we start graphing them, they're going to come out to be this shape. And I'll show you a little bit more in Desmos as well. Okay, they come out to be this shape. Now, what is so important about this shape that we're going to spend 6 weeks on it? Okay, so you might not recognize this, but this is the shape of many things that, you know, electronically or visually that you probably use very often, such as a flashlight. So if you look at a flashlight, it's a three-dimensional version of this, but there's a bulb, right? And behind the bulb, there's something that's reflective. Now, how come it's always in this kind of curved shape, right? How come when you point a flashlight at something, the light goes to where you point it and doesn't just go random places? So because we folded this in such a way where it was always perpendicular, which means 90 degrees, that this bulb, no matter where the light shines, if it goes here, the light shines here, the light shines here, the curvature of this shape makes it bounce off and go straight. Right? So no matter where the light hits this parabola, it will bounce off at the perfect angle and go exactly straight out. Okay? And that's the power of this particular shape of parabola, is that no matter where the light hits it, even if it hits it over here, right, the light will bounce off and go exactly in the same direction as everything else. So you can focus anything to a certain direction that you want it to go. Okay? So that's the power of what a parabola is. Now you guys also see, you know that with a flashlight, it's not magic that the light actually goes where you point the flashlight. But if you just made any old normal curve and you just kind of made it up, well, if it's not perfect, if it went out this way, it would go this, the light would be going all sorts of directions, and you'd point a flashlight someplace, and it wouldn't actually make that light up because the light would be bouncing in all these different directions instead of going actually straight out. You also see this on like DirecTV and dishes outside of houses, apartments, stuff like that. They always have a curved shape, right? And they have that thing that's kind of coming out, that's connected to it, and it comes out so far, right? It's the same thing. It's bouncing a signal hundreds of miles away. It actually has to point and has the signal go towards that direction. So if this parabola or that parabolic dish is not perfectly engineered to be exact, the signal won't go to where it's supposed to go hundreds of miles away. It's pretty remarkable you can send a signal 100 miles away if you just have the right type of shape. And this, you might think that thing that's popping out is the thing that's actually sending the signal, but really it's sending this way, but more so it's bouncing it this way, which sends many signals over and over and over repeatedly many times, so it eventually gets there. Maybe not every single one of these will get there, but enough will get there that the signal gets through. So this is actually sending it, bouncing it off the dish to send it out. It doesn't just go out from there, and that's why it's in that shape. It's not, just, oh, that's a nice shape and it looks nice, so we made it that shape. For it to actually work, and you can see any radar tower, all those cell phone towers that you see, they always have a disc with something in the side. So it's the same thing for receiving it. If you want to receive a signal, it can come in this way and it bounces off here and it hits that focal point. No matter what angle it hits it at, it always goes to that same focal point. By the way, for that reason we call this the focus. That little space, that little right there in the middle, it's called the focus point. And that way you can send or receive any information or light. Like they do the same thing with lasers, they do the same thing with fiber optic cables. Like, how do you send this light all the way over there and make sure it actually gets to the exact point it needs to go to? There's some focal point, and there's some device or some shape that makes it bounce. No matter where it hits here, it all bounces to that same place no matter what. So it's a very, very useful tool that we've been using for a very, very long time, beginning with radar, but now it's like satellite dishes, taking pictures from planet Earth, and you can get millions of miles. How can you take a picture millions of miles away? Like, you ever see those things on the news every now and then? Here's a new picture of a galaxy that's 100 million miles away. That would take us, if we tried to fly there right now at 1,000,000 miles an hour, it'd take a billion years. But we can take a picture from Earth, okay, using something like this. And you see these giant dishes, and they're huge, and they bounce all this information, off a greater parabola-shaped disc, or paraboloid they're called, and they can actually take pictures from millions of miles away. So that's what you guys are going to be graphing and learning how to do. Now, actually finding this point to find the focus and how that part works, that comes in Algebra 2. We're really just going to focus on how to graph the parabola itself, what the properties are, how to make it wider, skinnier. Because if you want to get something that's millions of miles away, you see those satellite dishes are actually huge. They're really go out here. Okay, if it's really close, it can be a lot smaller. So how small does it have to be to get something that's a mile away? How big does it have to be get something or send something from, a million miles away? So those all go into factoring this. So that's what we're spending the next 6 weeks on, and that's where we kind of began this week. Okay, I'll show you how that's all related to what we've been doing. Okay, so hold on to that, and here, there we go. Okay, let's first begin down here. One thing that we just saw on making our own is that there is a symmetric property to parabolas, meaning it's the same on the left side as it is the right, same on the right side as it is to the left. So if you know from the very beginning, if you know that you have one side, okay, you automatically get the other side free. It's like a buy one, get one free deal. Okay, so there we go. So if I know that, and it tells us that this is the vertex, it just means the highest or lowest point. If I know this is the center of the graph, and I know this is the left side, I automatically know the right side is going to be symmetrical. So if this is one away from the middle, there'll be a point one away up to the other side. If I go down a little bit, this point is 2 away from the middle. We also call that the axis of symmetry, right there. I know there's another point 2 away on the other side. You see how it stays symmetrical, the same on both sides. Now, when you draw these curves, you saw how it kind of came out. You should have like a U shape at the end. At the top here, kind of like a U shape, and then at the ends here, it keeps going outward ever so slightly. It will never be a U shape. Okay? Just at the tip here, by the vertex, it'll look like a U, and that's the vertex right there. Okay? But the ends ever so slightly keep going outward. Now, what happens if it was a U, and we were trying to do this like with a like a flashlight? You had a bulb right here. Well, if the light was shining right here, it just bounced back and forth, right? The goal, of course, for this is for it to bounce outward. No matter what, the light or the signal would be going outward. So if you had a U shape and you put a light here, right? If it hits here, it's just going to bounce within, and the signal will never go anywhere. So that's why it has to keep on going outward ever so slightly. Otherwise, the signal of the light will never leave this parabola. Okay. So you can see here we got a vertex. By the way, would you say this vertex is a maximum or minimum? It's at the top here. Yeah, it's a maximum. It's at the top. So I'm just going to give you a little bit of terminology here. It's a max. That vertex is a max. There's some questions here. Does it open up? Does it open down? Yeah, it opens down. So, and this is the extent of your homework tonight, by the way. Okay. Oh yeah, it opens down. I can see it. It's a maximum because, well, the vertex is at the very top. Okay. The axis of symmetry, it's right in the middle. Technically, the equation for it, again, this is the x-axis, right? So if you look at here, this is x equals -1. So the equation would be x equals -1 for the axis of symmetry, which just means the middle. Don't get confused with fancy language here. It just means the middle. Axis of symmetry is the middle. Okay. And we already plotted symmetric points. And we can say, what are the x-intercepts? Okay. Where's it cross the x-axis? Right here at +1. And right here at -1, 2, 3, at -3. Those are the x-intercepts, where it crosses the x-intercept. And what's the y-intercept? You guys know that one. Y-axis, 1, 2, 3. Crosses the y-axis at 3. And that's going to be the extent of your homework. Just do it a few more times. Does it open up, open down? Where's the middle of the graph? Write it in the form x equals. Okay, we already plotted the symmetric points. You can do that first, or you can do it number 4. Where's the cross on the x-axis, and where's the cross on the y-axis? Notice how there are 2 answers here. These right here, these 2 numbers are related to when you guys are solving this stuff. These are actually the x-intercepts. That's what you guys have been working on. The whole time, those are actually, when you're graphing it, where it crosses the x-axis. And that's why we're spending so much time on them for a whole week. Okay. Now, just want to go back up to the top. I want to do the other part first, because I want you guys, when you need to graph, I want you to figure out half the points. So do like 0 squared, obviously equals 0, so that's the point 0, 0. Right? 1 squared equals 1, so that's the point 1, 1. 2 squared equals 4, so that's going to be the point 2, 4. And so on. 3 squared equals 9, so this is going to be the point 3, 9. And only do half of them, because the other half is going to be identical using what we just looked at, using symmetry. So, go ahead, let's plot just half of it. Right? So we have 0, 0. We have 1, 1. We have 2, 4. And we have 3, 9. So now it looks pretty much like on the next problem that we did first. If we know this part, and we know that this is the center, we get the other side for free. Okay? We don't have to really finish this table and figure it out. We know it's going to be the same. Okay? So I can say, oh, this is 2 away on this side, and then go 2 away on this side. Up here, it's 3 to the right. I'm going to go 3 to the left as well. Okay? And you can finish the graph and not have to do as many calculations in the process. And again, when you draw this, nice smooth curve, rounded at the end, not pointed. Okay? And the ends go outward just the slightest bit they go outward. Drink your chill. So with that information, go ahead and let's see, look at the next one. Again, you could just start it off by drawing the actual axis of symmetry is useful, so you can count the squares easily. Right? So we can see there's a point 1 to the right here, so we just go on the other side. There'll be a point on the graph on the other side, completely symmetric. Go down to the next point, it's 2 to the right, so we'll go 2 to the left on the other side. And then, given that, we can draw our nice parabola. And it keeps on going outward ever so slightly. Never vertical, because then our light or our signal would never actually reach our destination. Okay. So try to make it the same on both sides as much as possible. Okay. Is it opening up or down? It's opening down. Okay. Don't worry so much about the infinity, negative infinity. It just means from top to bottom, with bottom being negative and top being positive infinity. So it opens down. Is it a min or a max? Once again, the vertex. It's a max, right? Still, there's the vertex right at the top. Okay, so it is a maximum because it's, and really that's a fancy way of saying it's at the top. And minimum would be if it's at the bottom, right? Nothing more. What is the axis of symmetry? Again, that's an x equals. So where is this red dotted line on the axis? It's just right at 0. X equals 0 in the middle. This would be positive 1. This is negative 1, so it's right there in the middle. X equals 0. What are the x and y intercepts? All right. So x-intercepts are here and here. So that would be 2 and negative 2. So write that down. 2 comma negative 2. I'm going to put it in these braces like so. We kind of did that when we had, what was it? Absolute value. Because there's 2 answers, right? It's not a coordinate. It's not 2 comma negative 2. Like That would be 2 comma negative. That'd be right here on a graph. That's not what we're saying. We're saying both answers are x. If you use parentheses, it means one answer is x, one answer is y. But these are just 2 x equals, so we use the braces. And the vertex, the y-intercept, happen to be the same, so it's at 4. Only one of them. So the y-intercept is at 4. Okay? So again, does it open down or up? Is a vertex at the top or bottom? Is it a min or a max? What is the axis of symmetry? What are the x-intercepts? There can be only one. Doesn't have to be 2. There can be 1 or actually 0. And then what is the y-intercept? Now I just want you guys to finish up 2, 3, 4, and do 5 and stop there, and we'll pick up 6. Okay, so just do only the problems that we just did that are similar to it.